So we discussed inference last time, just in one lecture, which is on exact inference. And to keep that kind of simplicity a little bit more forward, I'm going to also discuss parameter learning, also known as learning or parameter estimation, in the very simplest context, just to set the stage. In the future, we're going to really get into a much more treacherous and intertwined territory where everything becomes less kind of explicit and clean. But I think this is still a lecture where clarity and rigor it can be expected. So just to recap, when people are talking about the learning graphical models, usually this is the bigger picture of the story. You are given, you started to not from nothing, okay, from some knowledge already. For example, they give you a set of random variables which are named or indexed already, and then you are given some data sets. That's the simplest setting. The data sets are assumed to be identically and independently distributed. And also in this case, they are observed fully. Every random variable has an instantiation. And then the goal for learning in this context is to come up with these two things, right? One is called structured learning. You need to learn the graph, although in many cases the graphs are specified by people, but in theory, in principle, it is also possible to learn the structure directly from graph. This is a topic we're going to touch upon a little bit later in our causal inference lectures. The more common scenario is to use this graph and also this data, and then come up with these estimations of the parameters. Okay, in this case, the numbers in the conditional probability table. In case of an undirected graph model, you see the numbers in the potential functions. Okay, and there are a lot of scenarios, in the umbrella of under the umbrella of learning, and here I name a few. The most kind of a simplest case is called a completely observed graphical model. And again, there are cases on directed and undirected. If you're interested, you can go back to our historical lecture notes and found that even up to now, learning completely observed undirected graph model is already more than trivial. You need to somehow call subroutines which does inferences in a graph. I'm not going to say too much about that today. Maybe in the future we're going to touch upon that. And then we're going to see learning partially or unobserved graphical models, again in directed and undirected cases. And I'm going to discuss a particular algorithm, very often used for these particular cases today. Okay. And then, learning actually also could be generalized into many different scenarios. Not more than scenario, but the estimation principles. Typically, in the classical literature, when we talk about the learning of parameter estimation, it really means maximum likelihood-based parameter estimation. You want to estimate the parameters, maximize the likelihood. But this is actually almost like the default principle in the world of statistical machine learning or classical statistics. But modern machine learning actually already went beyond just MLE. For example, at least you can do Bayesian estimation, conditional likelihood estimation. But later on, there are different loss functions like margin-based loss, entropy-based loss, and so forth. Somewhere in the class, we're going to present a more kind of universal and standardized view of all that, so that all the different loss functions can be unified under something like a standard equation. We're going to see that later in the class. That actually goes even beyond this list. For example, in reinforcement learning, we sometimes rely on an intrinsic or extrinsic reward. Okay, this is another type of loss. And in adversarial learning, you also use an auxiliary function to test the truthfulness of the outcome. And that kind of adversarial score could also be the thing you maximize. So there are a lot of different scenarios in modern machine learning community. So we use the word learning, in a very kind of overloaded way to describe the process of estimating parameters for all that. There are only a very few scenarios people can say very, very concisely about what is happening or how to characterize the learning outcome. For example, do they give you a consistent estimator and so forth, which is the case we're going to discuss today. But again, in more modern, practical, engineering-oriented machine learning, those characterizations may be compromised. Okay, so let's start from the simplest case where we want to do parameter estimation for completely observed graphical models given the structure, in particular Bayesian networks, direct graph models. Okay? And this is a single page summarizing what's going on, okay, in terms of the principle. You are going to start from a graph that is designed by experts. You are going to take the ID assumptions of the data. And then we begin from analytically write down the loss function, which is the likelihood of the data as a function of the parameters. And thanks to our definition of the Bayesian network, we know that the probability can be expressed in a product of many local terms. Okay? And we use the log of the likelihood as the loss function. And as we'll see very soon, for arbitrarily big graphic models, they all, are built on, some smaller building blocks. In fact, here you can see these are little building blocks, okay? And I'm going to just mention two building blocks that I'm going to just, gloss over the details and present, just point you to some reading materials at the end of the lecture that I can go through, which are, very, very specific case by case. For example, one type of graph model is a singleton node. Okay, you have only one random variable. This occurred in the graphic model context as the root, for example, in a tree or something. When you want to estimate a marginal distribution of that root node, you may run into this particular case. And this is known as the density estimation. And as I'm going to mention in a second, these typical distribution families that we use, such as a Bernoulli distribution in this, a multinomial distribution in this case, is an instance of the exponential family distributions. And traditionally, people need to work out all these equations, okay, for every distribution family. For example, here you can see the definition of the likelihood of a particular outcome, which should be expressed in this form, a product of multiple probabilities of the outcome, okay, selected by this X indicator, which is indicating one of the events will be true, others are false. And I'm not going to walk you through all this, but at the end of the day, you get something very familiar to you. The frequency of every phase is going to be the count, the frequency, the parameter of each probability is the frequency of the outcome. And you can imagine that for different distribution family like Gaussian or others, you have this kind of work to do to derive all the equations, which I gave you quite a few examples at the end of the lecture. So I'm not going to discuss that now. I think it's covered either in 701 or some other more fundamental statistical courses. Even for two-node graphical models like this, where you use it for graphical, for classification and clustering, again, there are instances that require some modest amount of derivational work, and you will find that in here. Okay. So the purpose of this class is to give you not just discussions on specific instances, but to give you some kind of a bigger picture about what is the generic rule or the patterns of such estimations, and then how do you in the future reproduce or reuse this kind of technique for other models. So that gets us to the exponential family, which is a very, very broad family of density functions for different types of random variables or probability distributions. So it's a basic building block. Again, this class is interested in building blocks rather than specific instances because there is no way to exhaust all the instances. So this is the definition of an exponential family. It has this very interesting structure, exponent of eta as a vector and times t as another vector. T is a function of your random variable x. And t is known as the sufficient statistic, and the eta is known as the natural parameters. Okay? And the point of notice, these two terms, which are the most important terms in this whole thing, are interacting as a dot product. They are linearly dependent on each other or interacting each other. And then you have another thing, which is the log normalizer. You have another thing, which is the other part of the input variable, which has nothing to do with the parameters. Okay, they just exist, standalone. Okay, and why it is interesting to study this, as you will see very soon, the estimation of the parameters eta will only requires information about this t of x and nothing else. That's the beauty. Okay, and that gives you some kind of a generic kind of process of doing parameter estimation. And the members of this family includes almost all the things that you ever heard about in practical statistic of probability or statistical modeling. Okay, Bernoulli, multinomial, Gaussian, Poisson, gamma, t, and so forth. Okay, it would be very hard for you to name something that is not in this family, in fact. Okay, all right. So let's just look at a few examples of why, for example, Gaussian is a member of the exponential family. Okay, so this is the way we write down Gaussian distributions, right? It's it defines on two parameters, which we call them mu and the sigma, mean and the covariance. These are, by the way, also known as the moment parameter. Previously, we said exponential family is defined by canonical parameters. So these are two different sets of parameters, but they are related, you will see. And we can rewrite it, okay? And after some rewriting, you will see this expression of the same distribution, which exposes you the so-called linear dependencies between some forms of the random variable, such as xt transpose and x versus the parameter. Okay. And now if you take a different view of the parameters, rather than calling mu and sigma to be the parameter, but if you do this, you call sigma inverse times mu to be a set of the parameter, and this one is another set of parameter, then you can pretty much rewrite the whole thing back to the canonical form of the exponential distribution. So in here, I have a vector of parameters, okay, eta, and here is the specific composition of the vector. The first half is a vector due to this operation, and this one is called the vec. This, what is that? Well, it is just to linearize this matrix, put the rows and columns stack on top of each other, okay, make them into a vector. Then you have a gigantic vector in here, which are n squared plus n long, okay? And then here you have the t, which is a function of the random variable. Again, this is the x vector itself, And this is the vectored form of this outer product of the x vector itself. So you can hopefully convince yourself that these two guys, t of x and eta, are of the same dimensionality. They can actually dot product on top of each other. Okay? And these are the a's and these are the h. So by doing so, I kind of forced the very symmetric and beautifully looking Gaussian distribution into something that is more like a exp of eta times t plus a and so forth. That. Okay? Just by doing some algebraic rearrangement. You may ask why I do that. We will see in a second. One more example, multinomial. You know what is multinomial, right? It's the probability of describing a discrete event. Okay? And that's how we write down multinomial. It is, yeah. You basically just multiply together, the probability of every event raised to the power of the indicator of that event, which causes you to select one of the pi's to be the outcome, right? You know that trick. Because x is either 1 or 0, therefore if it is 1, that pi is selected. If it is 0, that pi is basically exponentiated into 1, and therefore it vanishes. So how do we rewrite? Well, here is a little bit a kind of a cumbersome way of rewriting it. Again, I'm not going to explain that in detail. You can work it out if you are curious about. It basically presents itself in the form of a product or a linear combination of all the x and also some form of the parameters. It's a little bit weird in here. You can see that the summation is now from 1 to k minus 1 rather than all the way to k. Why? Because the parameters in the multinomial distribution is constrained. They have to sum to 1. Right? How to incorporate that constraint? Well, it's better to just name pi of 1 all the way to pi k minus 1, and then make the last one to be 1 minus sum of pi k I equals to 1 k minus 1. Right? That basically automatically gives you the way to constrain it. Okay? And then, you can, after some rearrangement, you will see that this distribution now is expressed in this way. It's a little bit ugly, but once you do some cleanup, you define the eta to be of this form, and you define the t to be of this vector, you recover the exponential family canonical form. Okay? So why I bother to kind of let go this beautiful expression and go with such a more hairy and sometimes even ugly expression? Why that's the case? Well, it's because inside the exponential family, the data and also the parameters are now very, very cleanly grouped into two terms. One is called the tx, the other is the eta, regardless of what kind of a family you use. Okay, that's actually very, very important. One importance is the following. There is a very standard way to now generate moments for all exponential family distributions. You have the a, which is a function of the parameters, of the natural parameters eta. You take a derivative of a with respect to eta, you get such a term, the expectation of the sufficient statistic, or the tx. If you take a second order derivative, you get the variance of that. So this is called the first order moment. This is a second order moment. In fact, you can get all the way to third order, fourth order, or nth order moment just by keep taking derivatives of that. Okay? So there is a standard operator that allows you to get moments. And moments are very important, right? Because in many distributions, the moments correspond exactly to those moment parameters, like mean and variance and so forth, right? So parameter estimation or moment estimation, can actually analytically be expressed as a standard operator that comes from the derivatives of the log normal function. And also, it exposes you a clean analytical relationship between the natural parameters and the canonical parameters. Okay, in here you can see, this is the expression of the the moment parameters mu, which is the expectation of the first order, which is the first order moment. Also, just for free, you can also conclude that the A of eta is a convex function because it results in the second derivative results in a positive number, which is the variance, right? And you can also work out, given specific form of the A and the eta, this psi function that relates the eta to the mu. And by the way, this relationship is one-to-one mapping because it is a convex function. Okay, therefore you can switch back and forth between canonical and the moment parameters quite flexibly. Okay, and that basically gives you hopefully a unified picture about the MLE estimation, maximum likelihood estimation of the exponential family. You begin by writing down the likelihood of the data, which now uses the exponential family distribution form. So the only differences between different distribution is your precise kind of form of the eta and of the t. Okay, and then once you set the first order moment to 0, you get the mean parameter estimation, and otherwise you get second order gives you the variance estimation if your distribution needs a second order moment, such as the Gaussian distribution. So now, why such a unified view can be interesting and can be practically important and useful, right? Well, the core behind this idea is known as sufficiency. The exponential family distribution exposes you very, very explicitly, the relationship between the parameter and the data, in a linear dependent fashion, and also, it tells you what kind of transformation or form of the data you need to take care of for preserving basically the uniqueness and the identity of the distribution. Do you need to, for example, save all data points? You collect, for example, 1 million data points. If your boss tells you that, hey, collect these points, and my goal is to get the estimation of the natural parameters, then you could be smarter in terms of the storage. Okay, for example, storing just the sufficient statistic of those data, and ignore everything else. That's doable. So this view is expressed in this graph, and it gives you different ways of viewing the dependencies relationship between these three quantities. So here we have the quantity data, and here we have the quantity called the parameter, and here we have the sufficient statistic. So in the Bayesian view, typically we say we're going to draw a conclusion on the parameter given the data. Therefore, there is a dependency of the parameters from data in that way. You always write down posterior. Okay. And in the frequentist view, they view data as generated from an unknown true value of the theta or of the parameter. Therefore, you write down p of x given these two things, right? And by the way, the theta impacts the x only through that, because after all, your family, your distribution is an exponential distribution family. Therefore, the theta alone isn't sufficient to cause to define the distribution. You need to have that Tx together defined. Therefore, these two jointly define that. And the same thing, from here, it does not directly define theta, but through that as well, right? And a view that reconciles these two, to make them both sensible is known as the Neumann's factorization theorem. And that actually exposes the sufficiency and highlights the role of T. Basically, T is playing such a role that it deseparates the X from theta, okay, in either direction, okay, meaning that, for writing down the whole thing, you basically need to really know this part and that part, okay. Okay. A few more examples. Okay, so now at least density estimation for a single random variable for many different distribution families, I hope you can recognize that they can all be taken care of by working on sufficient statistic and moment matching using the exponential family distribution family principles. Okay, you need to remember one algorithm now. Move on to a little bit bigger graphical model, 2 nodes. As I said in the opening, there are many instances I can work on. And again, I'm not going to work on specific instances. I'm going to give you, again, a general picture of that. The general picture is known as the generalized linear model, okay, which builds on our knowledge of the exponential family distribution. So here is what happened in many of these 2 nodes graphic models, okay. We know what is a linear regression already, right? Linear regression is about y equals to, say, the theta of x plus some noise, right? We also knew what is what could be one of the common discriminative linear classifiers from your 701, 601, or other introductory ML courses. Can you name one? A linear discriminator classifier. What? LDA? You mean latent diffusion application? Linear discriminant analysis. Looking at the name, it's not already a model, right? But we don't call model analysis, right? Logistic regression. Yeah, I want you to form the habit of being very, very rigorous. Just like in my opening lecture, I say, don't tell people I solve problem by graphical models, because you're offering this whole class to a particular problem. That's not the solution. Okay, let's be very explicit. Yeah, logistic regression is one of these. Can you name another one? I just want to be a little bit fun and test you a little bit. Do you know another linear discriminating classifier? SVMs, right? Yes, right. So we can name a few, but these two are being the most famous one, right? So let's look at what is logistic regression. I believe it is about defining the conditional probability of y equals to 1 given x using some kind of logistic expression, right? I believe it is 1 over 1 plus e of minus theta tx, something like that, right? So these two looks to be very different. The outcome is different. One is a continuous, the other is a discrete, right? And then the function also is different. One is a linear. This one, well, it is not linear, right? It is actually taking a strange shape like that. But why we now call them generalized linear model? Because there is a key component that exposes the linearity, and then the nonlinear part is taken care of by some other Blanket function, so that we can still use linear technique to work on all this. That's the point behind generalized linear model. So let's take a deep dive. So for all these models, one observation people made is that you can take expectation on y. It turns out that it's always a function of the linear combination of this, theta and x. Okay, This is a commonality you're going to see to yourself very soon. So in here, there are a few things to ask. I'm taking expectation of y. Therefore, implicitly, I'm saying there is a distribution on y, given the x, right? So it says basically there should be a p of a y given some kind of a function of x. So what is that? What is the conditional density of that? Well, can you give a guess? What is that? What is that conditional density of x? In the most general form, you couldn't be wrong if you say that. Well, 1 minute ago, we just said it. You could introduce an exponential family distribution to be that. Okay, that's exactly what people did. By using one member of the exponential family distribution, you are good in covering pretty much all the needs to describe the condition of y. Y given what? Y given x, but not x itself. It is the f of x plus something else. And this is known as the response function. Basically, when x enters the system, okay, it has to be treated in a certain way. And in this case, it is treated in the linear way. Just multiply dot product with a vector of parameters. And in this way, it is treated in a logistic functional way. It is multiplied with a vector, then, a few more steps. But again, it is still a function, right? And generate different responses. One is a linear response. The other is a kind of a logistic response. That basically gives you the generalized linear model, all the basic building blocks. Okay, so we basically define the conditional mean of x, okay, which is called mu, to be equal to the response from the input due to the f function. So f is known as the response function, okay, and psi is the signal, due to the input augmented or weighted, treated by the theta parameters. And the observation output y is now characterized by the exponential family distribution. Okay? And then by different choices of the f and the p, you pretty much covered all the linear distributions, the two nodes graph models that we run into. So let's look at example. This is the linear regression, right? And this noise typically assumed to be Gaussian, then your conditional is this. Isn't that a member of the exponential family model, right? And the logistic regression, same thing, I already wrote it. Right? So these are just two instances. In fact, we have a lot fancier instances, like this, Markov random fields. Well, you don't see y here, but obviously this is an exponential family distribution, right? And if you want to say, I want to have a label of y for the whole thing, given this, then that gives you the Glean model. This one is also like that, and this conditional random field is also an instance of that. Okay, you can see it's very clear here and here. Okay. All right, so now what this model really entails and why it is, again, a excellent template for many instantiations. What you see is a very simple modeling principle that you begin from data and you want to assume a set of parameters, which of course is to be estimated in this class, and then they interact linearly to form a signal, psi. Okay? And then they are going to be turned into the mean parameters of the conditional of the output using a response function x. Okay? And the main parameters and the canonical parameters are related by a psi, function. It's a transformer. It's an inversible function relating mu and u, and we knew that, right? We knew that this is the key where different distribution instances, say Gaussian or multinomial or others, can utilize different forms of effect. You have a flexible here. You also have some flexibility of combining the inputs. And then using the exponential family, you get y. Okay, so very, very mechanical way of pipelining the synthesis of a model. Okay, and that's where you arrive at the end. Okay, and as you can imagine that if you work on this form instead of say a multivariate Gaussian, a Bernoulli, and so forth, you are in the land of a very generic and universal derivation, and then the rule can be used in many places. I'm going to show you the rule exactly in a second. And people sometimes, because of this clear exposure of the response and also of the mapping function, you can imagine that you can cancel it, right? What if f equals to the inverse of the psi? Then this guy, psi, is going to be directly the natural parameters in that exponential family. That will save you a whole lot of burden, for the derivation, right? So this is known as the canonical parameter, okay, which is such a phi, psi that they cancel the impact of the response function. Okay. Well, is that good or not? I don't know, but at least analytically it makes your life a lot easier, and sometimes it will still give you sufficient modeling power. Okay. Okay, so these are a few examples of the response function, and let's look at the result of how to use a natural response. So this is a pretty straightforward result. Remember now that originally I need to have this eta times the y, and now the eta is this one, because the f and the psi cancels each other. Therefore, this linear response or signal is directly functioning as the natural parameters, okay, of the exponential family distribution. And that helps you a lot in defining a very simplistic conditional likelihood of the output given input. And then what you need to learn amounts to only learning the theta itself. And you can take a derivative of the likelihood on top of versus the theta. And then what you have is a simple generic learning rule, okay, which is this. And that gives rise to the online learning algorithm for canonical Glean models, okay, where you use this as a gradient step, and you do basically gradient ascent like this with a learning rate. Okay. Any questions so far? Yeah.
How do you choose the f and psi functions?
How do I choose the what?
F and psi in the previous slide. How do you choose these functions?
How do I choose these functions? Let's say this function, eta.
Yeah, psi.
The psi of that.
Yeah.
That's a good point. You basically are given choices already, say multinomial and Gaussian and all that kind of thing. You could also just write your any analytic form if you want. That's possible, which will result in a pretty complex A, because that's the normalizer. You need to make sure that they wrap whole thing back to 1. And people don't do that. People go the reverse way. They even don't want to choose the psi at all. They will just use this, so that you don't need to choose anything. Okay, that's another point. Yeah. All right. So this is an algorithm which works for any Okay, literally any Glean models. That means the logistic regression, the linear regression, and a few other things like CRMs and all that. They can all use this. This is one of these algorithms. It is a stochastic algorithm because here you have a summation of n data points. Here I'm using data points one after another. Okay, therefore it is online learning, incremental, very, very easy to implement. Of course, the performance can sometimes be slow. The convergence of a stochastic gradient could be slower. The alternative is to use a batch algorithm. And one of the best batch algorithms is called the Newton algorithm, right? The Newton's descent. But in Newton's algorithm, you need to compute the second order derivative, of the loss versus the parameter, which is known as Hessing. Okay, and where I derived it already. And analytically, they look very, very nice. Okay, this W is a matrix where you need to fill in the on the diameters, the first order derivative of this thing. Okay, this is requiring you the knowledge of that phi function. Unfortunately, that one you have to deal with that. It cannot cancel anymore. Okay, because it really comes from the second order. Come from here. But again, with our current library of, remember we have a library here that gives you different forms already, and you can just go look a catalog and still get that. So it's doable. Okay, so this one leads you to a batch learning algorithm just by taking we have Hessing already. We are going to look at the Newton method. The Newton method requires you to basically utilize the inverse of the Hessing and also the Jacobian, the derivative of the loss function. And that gives you this form. Okay. There are many different names for that. One of the names is called the iteratively weighted least square. Now it's becoming a little bit less important to really dive into the essence of these names. But they give you some insight about connections to other algorithms. For example, one of the insights is that if you just kind of dissect the equation, from this update rule, you actually can see that it is equivalent to solving this particular problem, which is very, very similar to the original least square loss between output and input. But in here, the output Z is actually a reweighted version, and this one is also one of the weighting matrix. So just very hairy, but that's kind of where the name comes from. Okay. But the point here is not about just diving into all these different details. It's about, again, the spirit of using exponential family distribution and Glean model to derive something very, very generic. Okay. And remember, one node graphic model and two node graphic models are the building blocks of bigger ones. So therefore, we are having some very, very universal building blocks for learning in this case, okay, for graphic models. Okay, so now let's look at instantiations. Remember this thing. This is our design principle, and this is the model. And by plugging in our learning rule originally, here is a relationship between the mean and the moment and the natural parameters. You can actually have now the expression of the relationship analytically. Then computing this should be very trivial. Then you plug in that W like this. Okay. And linear regression, same thing. In here, in fact, that W matrix is kind of trivial. It becomes identity, and you can use, again, that same algorithm to do the learning. Okay, so very, very quickly that we already went through these two cases. I covered, I believe, at least 3 or 4 models that you will ever run into. And remember, the simple graphic models are building blocks of bigger ones, right? Here are the bigger ones. And in the bigger ones, each of them is like this. And the wishful thinking is that you probably could just instantiate each instances of that from what we learned earlier as the generic solutions, and then get a trivial estimation of that. And here is just a more kind of graphical illustration about what can happen, right? Once you have this fully observed model and you write down the likelihood, your log of that will lead you to basically work on this model, that model, that model, and that model, right? You may ask, is this one different from this one? Is this going to be still a clean model, or we need yet another model to handle? We have two parents now. Should I say something about or not? Well, I can say a few words. I guess there are maybe two scenarios that this can happen. Typically, when you have two parents, they usually could join force and cause a joint effect by additive effects, right? Or multiplicative effects. In this case, they are no different from generalized linear model, because additive effect literally means that they add to each other. That pretty much means one more elements in the linear effects. If they are multiplicative, what do? You put a log of that, they become still additive, right? The trickier thing, let me just put a note here just so that we know what we said, okay? The trickier thing is what we call a multiplexer. This word isn't not very common because people nowadays are not interested in defining very, very intricate and sophisticated models. They usually want to have a big end-to-end and just, push forward big data into that. But multiplexer used to be very popular, in the good old days. What is that? It means that the two nodes in here are performing different roles, asymmetric roles. This is maybe a few others. Let's say we have another 10 of these, are the effects. This one is called a multiplexer node, which are doing the job of selecting. They will be saying that it's almost like a gate function, a gatekeeper. They say that which of this is on, depending on the value of that, right? So this is actually another interesting relationship. I claim that it is also doable in terms of a GLAM model. Why? How do you actually analytically express a selection function? Do you have a sense? Here is the trick. Multiplexer function. I used to have a lot of fun in designing this. Suppose that I have the k, 2 to k x, or maybe from here, 3 to k are the effects. I'm going to multiply each of them. xi, I equals to 3 all the way to k. I have all of that. And the first one, x2, is a selector. What do? I will do this trick. A delta of x2 and I. Right? If x equals to 3, then the delta will be 0 for others, but it will be 1 for 3. Right? So by doing this, I will basically combine all the inputs in an asymmetric way. And you know what? Now I take a log of that. I still have a Gleam model where some of the sufficient statistics is a log of x. Some of the other sufficient statistics is the x itself. Okay? All right, this is not what I plan to say, but I hope this is kind of interesting. So at the end of the day, you are going to run into, again, these many local estimations of conditionals, and then you can use the same trick in the GLIM or in the exponential family distribution, and chances are you're going to get these kind of simple estimators as the mean estimations. Okay. All right. Here's a summary. We went through learning single node graphic model and the two nodes graphic model, and we agree that BM with more nodes rely on local operators, which builds off that. Okay, that's just a summary. All right, so now I want to jump quickly into the next major part of the learning, which is on partially or unobserved graphic models. I'm going to again give you another algorithm known as the EM algorithm. So we learned one algorithm already, which is the gradient descent or gradient ascent, okay, which applies to all log linear models. And in here, why we need EM algorithm, or different algorithm. So first of all, partially observed models are very, very popular, and in fact, maybe more useful, practical than the fully observed models. Here we see examples already. In speech, we use HMM, and we use the hidden variable Y's to model the semantics. Okay, and what you hear are just physical sound waves. In biology, you only see the present day species, and everything that is in the history should be modeled as hidden variable. Even for simple tasks like clustering a collection of points, what actually is done is that you have to give them some kind of labels. Maybe this is 1, this is 2, this is 3, and these are hidden, right? And let's just focus on this simpler model and how people would really mathematically treat it. And here's a model, right? So we observe X in terms of their two-dimensional coordinates. We don't observe their label, and we're going to instantiate a Z, to indicate that. And our goal is to now estimate Z given X. But our model is more than that. The model, once you have this graphic model, you need to learn what? You need to learn P of Z, right? And also P of X given Z. These are the two things I have to learn. Each basically depends on some parameters. But the fact that it is unobserved make the learning trickier than before. So how would the people, so far, for example, when we are learning model, we use a loss function, which is the likelihood. So what is the likelihood of the data under a mixture model? Just the likelihood itself. Well, without spending too much time to elaborate, this is a simple expression of the likelihood. In a second, in fact, in this slide, you will see where it comes from, right? It comes from this complete graphic model with a hidden variable Z and conditioning of X given Z. And we use a very simple assumption. Z is just a multinomial of discrete options. And this one is just a very simple Gaussian distribution with a different means and covariance depending on the label, the simplest possible setting. And then when you write down, the joint likelihood equals to P of Z times P of X given Z, and but this is just the joint probability of two random variables, one of which is not observed. What is your likelihood of data? Your data is only the X, right? You need to do a marginalization of the Z's, right? And that gives you this one. It's called the mixture model, and you can see, and it's very intuitive, right? Mixed model is now consisting of a summation of a weighted Gaussian modalities, okay? and each one is weighted by a pi, which is the prior probability of choosing every label. So we call the mixture proportion and the mixture components. So naively, how do you learn? By the way, these are the parameters in the model you have to learn, right? Pi, which is the a priori frequency of the label, mu and sigma, the mean and covariance of the component Gaussians. How to learn that? Well, here's a loss function. Maybe the simplest way is to learn the whole, maybe, how about we do this? Let's say pi, mu, and sigma k equals to 1 to big K. This whole set, we call them the argmax of this. So that's basically the most kind of a straightforward, kind of a no-brainer way of learning that, right? It will be difficult, as you will see in a second. And where is the difficulty? Well, when we see all the values of the graphical model, we have this very nice factorization law that allows us to take a log of the likelihood and then treat it two different subfunctions. One is only about z, the other is about x given z, right? And then when you take derivative, for example, when you take derivative of the theta z, you only need to worry about this part. Otherwise, you will worry about this part. They are not interdependent. Okay, it's very, very simple. But now, when you have a latent variable, your likelihood becomes a sum of multiple terms, and therefore your logarithm has to happen outside of the summation sign. Okay, and therefore here becomes your loss function. Compare this and to that, you can see a clear differences. This one is more complicated. When you take a derivative of the whole thing with respect to theta, you are involving that already, right? And vice versa. Used to be a big deal, worry people. Nowadays, people are less worried. But again, we are talking about a historical account here. I still feel this worry needs to be addressed. So why nowadays it's not worried? Nowadays, when you look, compute about neural networks, what algorithm do you use? Well, a backprop, right? Backprop is an algorithm that couples everything in the graphical models together. And whenever you swipe a particular parameter, that impact comes from everywhere in the graph, right? So people are not bothered. It's because it's not very useful even if you bother, because you can do nothing with that. Too many parameters are coupled. You are not going to prove consistency and identifiability, anything for that anyway. In the past, people ask you, is your estimation consistent? Is that really the maximum likelihood estimation? Do you provably arrive at a single solution? When you ask that, then those coupling will be very, very harmful for you to prove anything, right? So people like the fully observed scenario better. And in the fully observed scenario, you actually can arrive at this little estimations locally based on counting a subset of random variables. And just take one example. For example, in here, when things are observed, your calculation of the mean, for example, is taking this equation. So what does this equation mean? Z of k is the label of a particular point, okay, in one of the k options. And therefore, when you sum over that, it will give you only the label in k class. And these are the number of times the k instances take place. Therefore, this equation gives you a mean of those points which are in class k. Right? It's very intuitive. The mean of the median, or the mean of the points in class k should be defined by this. And this is to assume that your z are observed. What if the z is not observed? Can we still use this formula without going back to that very complex derivation where things are coupled? By the way, this derivation is possible because I assume Z and X are all observed. Okay, so that goes to a algorithm known as the EM algorithm, and I want to at least achieve the following effects. When you walk home from this class today, you should know what does E mean. Okay, E means expectation. Expectation over what? And the expectation using what? Okay, that's something I want you to remember. And M means maximizing. Okay, maximizing what? And maximizing with respect to what? Okay, so these are the two sets of questions that we want to answer today. Anybody play with k-means before? Raise your hand if you have played with that. Great, that's very, very comforting. Tell you what, it did happen to me that we knew certain, very, very senior students in our own department MLD who are in their senior PhD years, never run k-means before. Okay, people are getting too advanced already so that they forgot the basic. And maybe let me ask you another question. You know k-means. When you implement k-means, any trick that you use to get to a good answer? Do you run k-means once, or 3 times, or 100 times? Right. So these are the kind of street fight, dirty technique that people, good old day ML people have fun with. So here is k-means, right? You basically do something very simple. You start from an unlabeled bag of data, and you are going to guess some kind of centroids. Say you have 2 classes, then you guess 2 centers, and then you start to make assignments, basically of every point based on those centers, depending on a particular point, which center it is the closest. And then once you made that assignment already, you are going to recompute the centers of every cluster, right? So this is basically the counting function for that. And then the effect will be you started from nothing labeled, to 2 guess point of the center, refinement of the actually assignment of the label based on those first guess. Okay, recompute of the center based on the first guess, reassignment and recompute and converge. Right. So there is a iterative procedure where you need to get the label and also recompute the parameter. Right. So this is k-means. Now how about I make it a little bit softer, which actually gets you to the EM algorithm. Many of you probably know already. I still started from this. I'm still going to guess the 2 centers. But in this case, I'm not going to just only guess the 2 centers. I'm going to call the center to be a pair of mean and covariance. Okay, I use the center to define a Gaussian distribution. Okay, and then I'm going to now look at every point and compute the conditional probability of a point under this Gaussian versus that Gaussian. You will never get the probability 1 of one point being in one Gaussian versus the other. It will be probably fractional. Right? Maybe say this guy is probability 0.7 to that and 0.3 to this. In that case, I'm going to split up points, okay, and make assignments of this point partially to here and partially to here. That's the only difference. Okay, in k-means, the point either go here or goes here. In here, I'm going to give them the so-called soft assignment. Okay, and so the soft assignment is this. This is how we use to compute soft assignment. It's literally the conditional probability of a particular assignment given the center and the covariance of that particular cluster. Okay. And here, literally, we are doing inference. We are trying to compute the probability of a hidden random variable given the observed. Right? That's what we did in last class. Right? And this is known as the E step in the mixture Gaussian learning. Okay. Forget about this point. Where we get this equation is actually not through a random guess or a experiment. They actually are specifically a consequence of maximizing some other terms, but we are going to recover that later. Just view this as a counterpart of the k-mean step. Okay. In our Z assignment, we make a soft assignment. And then once we make the soft assignment, we are good to compute all the parameters based on, basically partial counting. Now your pi becomes a sum over all data points over the partial assignments divided by all the numbers. And likewise, the mean and the parameter and the covariance will all be computed based on the so-called soft assignments. This is the M step. Okay. So remember, this M step is a completely kind of analytical, an analog of the fully observed MLE. Right? In MLE, we assume Z are observed. Therefore, all you need to do is just to count the mu's belonging to that, the taus belonging to that cluster. In here, we pretend that we observed already those Z's due to our E step, and then they become a fully observed problem, and then we are going to do the weighted counting rather than just a discrete counting. Okay? All right, just to summarize, compare this and that. So in k-means, what you have is a discrete assignment, and I think I was kind of sorry. This should be k-means, and this should be EM. Okay, the k-means are using the discrete counts, and the EM are using the soft counts. Okay. Okay. So I've been very slow, but now I'm going to move quicker. What is the EM objective? I can tell you that because we knew this term is very difficult to compute because of this, coupling of, all the parameters in the summation. What we actually did, for the previous algorithm is to optimize something called a expected complete likelihood. Okay. In here, we take expectation of the complete likelihood X and Z, pretending that the X and Z are all observed. But because Z is unobserved, what we do, we are going to take an expectation of that with respect to Z, because Z is a hidden random variable. And to achieve this, we need to basically compute P of Z given X, right? And that's our inference step. We learned that in graphic models, we can infer any hidden random variable given evidence. Suppose the parameter is known. But here we have a chicken egg problem. Here we need to assume that the theta is known. And here we need to assume that the theta is given, to estimate theta, Z is given. Now we basically are calling this is a E step and a M step. Okay? All right, so now let's get down to the theory, why this is legitimate. Okay. Is that a pure trick or a heuristic or what? Okay, so back to the question. We don't want to work with this guy because it is causing computational difficulties due to coupling of the terms. Let's start looking at a different term, which is known as the complete likelihood, regardless of data being observed or not. Complete likelihood is factorizable, and the true likelihood is unfactorizable, right? So how can we basically take advantage of the complete likelihood even when variables are unobserved? We need to use a few transformations to connect basically this one with that one. Okay, how to connect that? So here maybe is the single slide that requires some mathematical insights. So to go back to the point. This one has all the nice properties of factorization and all that. It is not a legitimate loss function. Why? Because it is itself a random variable. We cannot use a random variable to be a loss function because it has the z here, right? And how to remove that random part is to apply an expectation to basically clamp down, that random part z. Okay. And it turns out that there is this beautiful relationship due to the Jensen's inequality. So we start from the log of the incomplete likelihood, okay, the marginal probability of the data. And up to here, it is an expansion of the marginalization. And up to here, it's a pure rewriting of the equation. Right? We are basically plugging this and that upstairs and downstairs. The Jensen's inequality basically says that there exists such a inequality. You are summing over, the log of the weighted sum of something is always greater than the sum of the weighted, the weighted sum of the log of something. Did you get that? So treat this as a target, right? So here you have the logarithm of the weighted sum of that. Why this is weighted sum? Because this is you can view this as a weighting function. Okay, P of z basically are numbers that is between 0 and 1 and all sum to 1. Okay, and in optimization we call them a convex combination of different options. So this basically leads to a convex combination of things. The logarithm of the convex combination of options is going to dominate the convex combination of the logarithm of that thing. Okay, that's Jensen's inequality. And algebraically, you can see this from the curve. Okay, this is the log curve. The log curve is always going to be above the sum of points taken on the log curve. Okay? So why this is important? Because if you can do some rearrangement of this term, and this one corresponds to a sum of two things, this part times the log of that is that expected complete log likelihood. And this part combines the log of this is the entropy of the Q distribution, right? Okay. And therefore, the expected complete log likelihood is not a random target of optimization. It is the lower bound of the true likelihood. So in maximum likelihood, imagine that you are pushing up a curve, okay, by optimizing the theta. Now I'm saying that you are pushing a lower bound of this curve by optimizing theta. Chances are you are going to still push up the original curve. Okay? Therefore, you achieve a similar effect of likelihood as maximum likelihood estimation, even though you are working with a surrogate of that, which is this expected complete likelihood. Okay. So in EM, what is really happened is that you are now instead working on the lower bound of the likelihood, which is known as the energy function. And the two steps, E and M, is literally doing this. You are going to now maximize the F function in the space of Q, all possible choices of Q of Z given X. Okay. And it turns out that we can solve it by trivially make a Q of Z equals to a given X equals to P of Z given X of the current parameter estimation. And then in the M step, you clamp that Q so that no uncertainty is present anymore for the random variables, for the hidden random variables. You are going to treat them as a fully observed model, and then you do the Q estimation, or do the theta estimation. That's the M step. So it's a coordinate descent algorithm in the space of parameters and in the space of models. Okay, so EM is a coordinate descent algorithm. It's not just a heuristic. Okay, it has the property of converging to the maximum likelihood answer of the model. So here are some facts, to prove a certain nice property. For example, I said already, the choice of the Q of t plus 1 being this guy guarantees you to actually close the gap between the lower bounds and that. Okay, and it is the optimal choice. And therefore, by plugging in that, you effectively are going to work with the term that I just mentioned about. And in the M step, because you no longer have uncertainty on Z with this, you are going to do the standard parameter estimation, under fully observed cases. And then you will be using all the tricks, such as sufficient statistics, such as the gradient and other technique that I mentioned in a Glean model and in exponential family models. Okay, so that collapses us back to, first of all, I think partially observed, now collapse to observed, right? So let's just map this thought process through a EM, and observed, through the factorization, goes to, basically exponential family and also Glean models. Okay, so that's basically how you reduce a kind of non-trivial generic learning task for graphic models down to the building blocks that we just used. Okay. All right. So the take-home message for EM is that you can really, take care of those, troubling conditions like missing, like incomplete, unobserved, and all that with a replacement of the expectation of their sufficient statistic. Anything that is missing, you will just plug in with their expectation of the sufficient statistic. Okay, and where to get that? Well, you need to use the inference technique from previous class to plug in that. And then you are going back to the fully observed cases, and you're going to do maximum likelihood menu for the fully observed data, like what we did in the first half of the class. Okay, so that's basically where we get this. That's the end. Any questions? Any questions? This is a little bit dense today, so I want to make sure that you really have a chance to. Maybe one question I want to remind you. Many trivial, superficial understanding of the EM tends to say the following. EM is about really replacing the missing value with their expectations, so that I will be working with fully observed data. This statement is dangerously wrong, okay? Because when you are replacing the data with their expectation, you may run into, the cases where you need to compute missing value of this form, a product or some other transformation. When you replace the data itself with the expectation, you will get to something like and that is not right. You have to do this. Because this guy is the sufficient statistic, the X itself may not be the sufficient statistic. Right? That's why the exponential family distribution kind of concept is very important. The way data interacts with a parameter is through the form of the sufficient statistic, not the data itself. And when such data are missing, it is their sufficient statistic that you need to recreate or replace with a surrogate, not the data itself. Okay, so this is very insightful. You will be seeing examples of that in our presentation of the hidden Markov model, where you'll see both the singleton and the pairs of sufficient statistic have to be estimated and expected. Okay, I think that's all I want to add.